Here's the Unit 4 review done by yours truly, Mr. Physics Teacher Guy. I could ask you, you could just look these things up in your notes, of course, but I think that Newton's first law and third law are super important to know. The first law is the one that says, there's different ways you could say this. Let me state it here, and I'll say what you absolutely need to include for it to be correct. So Newton's first law is objects will keep doing what they're doing unless they're acted on by not just a force, but there has to be unbalanced force. And objects keep doing what they're doing. That means if it's at rest, it stays at rest. And if it's moving at a constant velocity, it stays moving at that exact same constant velocity, same speed, same direction. So the key here is you have to mention that the force is unbalanced and that objects keep doing what they're doing, which means at rest stays at rest, constant velocity stays constant velocity. This is the law that's often stated out there in the world. What is it? An object in motion will stay in motion unless acted upon by a force or something like that. But it's kind of incomplete the way it's just bandied about there in the world. So we want to make sure that we nail it down well, mentioning the unbalanced force and both of the conditions, at rest and constant velocity. Those are our two conditions, right, for this unit. Balanced forces. At rest, forces are balanced. Constant velocity, forces are balanced. How does Broomball show this? Because in the start box, no unbalanced force. You can't say there's no forces on it in the start box. There's gravity and the support force from the floor. No unbalanced forces. So the ball stays at rest. And in the no touch zone, there are no unbalanced forces. So the bowling ball stays at a constant velocity. What's Newton's third law? Newton's third law is that since a force is an interaction between two objects, getting lazy with my shorthand here, between two objects. What does that mean? Well, that means that there's only one force. When two objects interact with each other, there's only one force. So object 1 experiences same force as object 2, but always in exactly opposite directions. This is that equal opposite. So same as with the first law, out there in the world, people say, oh yeah, for every action there's an equal and opposite reaction. That's a really terrible way of stating the third law, in my opinion. This is a nice way of stating it. So don't give me the action-reaction crapola there, please. Draw a qualitative, that just means no numbers, just names on the forces, force diagram for a skydiver falling at a constant velocity. Constant velocity means forces are balanced. So skydiver falling down, gravity on the skydiver from the entire Earth, and if they're going at a constant velocity, the forces are balanced. That's what happens, when you jump out of an airplane. You speed up for a little while, and then you reach your terminal velocity. Now, how could the forces on you be balanced? Because you're going so fast that the air resistance matches gravity, and then you start to fall at a constant velocity, your terminal velocity. Force of air on the skydiver from, let's actually call that a force of friction, so I can say air here. That's all. Car driving at a constant velocity. If car is going at a constant velocity, the forces are balanced. So I'm going to make my car going this way at a force of gravity on the car from the entire Earth. The force of, we're going to call this traction on the car from the road. And then this way there must be a force of like friction and air drag, just resistance stuff on the car from, we'll call that stuff. And this is the support force on the car from the road. So that's equal to that, and that is equal to that. Because it's going at a constant velocity. It means the forces are balanced. Draw a qualitative force diagram for a block that's accelerating down a frictionless ramp. Ramp. That means your axes need to be tilted. Of course, gravity doesn't care. And it's still straight down. So that's a force of gravity on the block from the entire Earth. Let's break that up into its components, because that's what you do. That's my right angle right there. And then, although it's accelerating, it's not accelerating in this direction, right? It's going down the ramp. So the support force still must be balancing that. Normal force on the block from the ramp. And that's it. There's no friction force, so this right here, there's your unbalanced force. That's why this thing is accelerating, not at rest, not at a constant velocity. How about a car accelerating up a hill? Make the hill go that way. Force of gravity on the car from the entire Earth. Break that up into its components. And then what else we got? Well, there's going to be a support force, and that support force still has to match this. Force normal on the car from the road. And then it's accelerating up the hill. So there's a couple different things you could do here. You could think about, I think it was the last problem that we did on force diagrams 5 here, where we had the two forces. There was the gravity down the hill, but then there was also the resisting forces. You could put that in there if you want. That like other force of friction on the car from stuff. You could put that in there. I'm not going to stress that too much if you left that out. Then if it's accelerating up the hill, that means there's unbalanced force. So I'm just going to exaggerate that, make sure it looks like it's more than those. Force of, call that traction again, on the car from the road. Right? So balanced in the up-down direction, but more up the hill because it's accelerating up the hill. All right, number 5, a 2,000 kilogram truck pulls a trailer. I guess since it says truck here and then trailer, I think I'm going to make them go this way and put the truck here and the trailer here. If you did it the other way around, that's fine. It doesn't say. So this is the truck. This is the trailer. As soon as you see this, I'm probably going to ask you something kind of like this on the test. As soon as you see this problem with the two different objects, you have to think to yourself that this is going to be something like a Newton's third law problem. There's got to be some kind of equal opposite, like force of truck on trailer, trailer on truck. Right? There should be somewhere in your diagrams, you should be looking forward to that, the equal opposite thing happening. All right, so let's see if we can get there. So 2,000 kilogram truck, force of gravity on the truck. Trailer also starts with TR, so I think I've got to be careful about my abbreviations. From the entire Earth, that is 20,000 newtons. This times 10. And then the support force on the truck from the road. Let's see. The trailer pulls back on the truck with a force of 500 newtons. So this is the force of, call it pull, on the truck from the trailer. So there you go. There's the two objects that are involved in this. And they, we are told that that's 500 newtons. Okay, so right off the bat, I'm going to just jump over to here, because if this is the truck on trailer, then there has to be an equal opposite trailer on truck. So this is force, pull, switch those on the trailer from the truck. And of course it's the same force. Right? So that is what we call a Newton's third law pair, equal and opposite. There's equal forces. You can see those switched the order right there. This is the force on the trailer. This is the force on the truck. But it's one force. It's an interaction between them. Okay. In addition to the trailer pulling back on the truck also experiences 700 newtons of friction. All right, so that's going to be back this way, force of friction on the truck from stuff. It's not the road. It's not grinding along the road. It's like the axles and maybe some air resistance, all that. So we'll just say stuff there, like we have been doing. And that's 700 newtons. Now, if we're going at a constant velocity, then that traction force on the truck from the road has got to be the sum of those. All right. The trailer pulls back on the truck. 700 newtons of friction. So I think we're good here. We just need to finish this one. So this is the force of gravity on the trailer from the entire Earth. And that is 2,500 newtons. So there's got to be a support force on the trailer from the road that balances this. And force of friction on the trailer from stuff, which has to be equal to 500 newtons. Now, if you're looking at this and you're like, well, wait a minute, like it didn't say that there was friction with the trailer. Well, there has to be. I mean, what else could this be? If we're balanced forces going at a constant velocity, that must be true. So I'm just going to go through and put some more tick marks on things to show what's equal. This is 500, and so is this. Right? I can't do any tick marks with that and that because this is equal to the sum of those, but I can do, I could do 3. Why am I doing 3? Because I used 1 and 2 over here, so I got to move on. All right. That's what those look like. All right. Lab is set up like this, and the readings on the force sensors are 120 newtons at 30 degrees. That's the one on one side, and this looks like the 30-degree angle over here. Doesn't matter which one you put on which side, but that looks like a smaller angle, and that looks like 45 there. So this is 1.2 newtons, and this is 1.47 newtons here. What are the horizontal and vertical components of the first force? That is, the first one that's mentioned is this. So it's 1.2 newtons, and this is 30 degrees. So this is going to be 0.6, because the sine of 30 degrees is a half. You can just do that little game where you do both. 1.2 times the sine of 30, 1.2 times the cosine of 30. You get 0.6 and 1.04. And this should clearly be the longer one if your diagram is any good. So there's those. How about the horizontal and vertical components of the second force? Well, that's got a magnitude of 1.47 newtons, and that's a 45-degree angle. You know what that means? So the same as each other, but don't take my word for it. Put them both in there if you want. So 1.04. If you're thinking to yourself, oh, hey, that's coincidence, that's the same as that. Well, they had to be the same as each other because this thing is, the forces are balanced here. So what's the force of gravity on the unknown mass? So I'm going to make a force diagram kind of like that lava problem that we did not too long ago. Make the force diagram of that little junction right there. So here I've got this force, and I've got all my components. So let's see, what did I have? I have 1.04 here, 1.04 here, 1.04 here, so those are balanced, and 0.6 here. So that means that the force of gravity on the unknown mass, which is what we're looking for here in part C, is the sum of those two. And then what's the unknown mass? If you want to get to mass, if we have mass, we multiply by 10 to get this. So if you want to get back to mass, you got to divide by 10. So the mass is equal to this divided by 10, 0.164 kilograms. And then if you want to switch that into grams, that is 164 grams. That doesn't mean anything there. That's stray mark. 164 grams. All right. Number 7, a 1.5 kilogram book slides down a ramp that's angled at 25 degrees at a constant velocity. Forces are balanced. So it's sliding down. That makes my brain want to make it go this way. It's on a ramp, so I got to make that at an angle. Then I'm going to put my other axis in. Then I'm going to tilt it back for a sec and put in the force of gravity. And then I'm going to label that force of gravity on the book from the entire Earth, and that is equal to 15 newtons. Multiply that by 10. And I'm going to break that into its component parts. That's where the right angle is. So what do we got? 25 degrees, that's the little angle going to be down there. So 15 sine 25, 15 cosine 25. So I got 6.34, that's the smaller one, and 13.6. Okay. That looks right. If this is 15, that's what those are. And what else do we have? It's going at a constant velocity, so all the forces are balanced. And the support force on this book from the ramp is going to be equal to 13.6 newtons. And there's got to be a friction force, otherwise it would be speeding up down the ramp. And that friction force on the book from the ramp is got to be equal to 6.34 newtons. All right, that's a nice looking force diagram there. And I think we should be able to answer these questions now. What's the magnitude of the component of the gravitational force on the book that is perpendicular to the ramp? So here's the two parts of gravity. This is the one that's perpendicular to the ramp. So that was the force of gravity times the cosine of 25 degrees. That was 13.6. What's the component of the gravitational force on the book that is parallel to the ramp? So parallel to the ramp in the same direction of it, that's the force of gravity times the sine of 25 is 6.34. And then what's the force of friction on the book? Well, the force of friction had to be equal to that. Also 6.34. That's pretty close to what your test is going to look like. So practice those problems. Just watching me do that once is not going to put you in great shape. You got to go through and practice doing them yourself. Go back, practice some of the force diagrams and stuff from the other sheets that I gave you.